Welcome! Today we're going to learn about mathematical identities. An identity is an equation that is true for all values of its variables within its domain. Unlike regular equations that are only true for specific values, identities are always true for any valid input. Let's look at a classic example, the square of a binomial identity. Let's verify this identity with some actual numbers. First, let's try a equals 2 and b equals 3. On the left side, we have 2 plus 3, which is 5, squared, giving us 25. On the right side, we have 2 squared, which is 4, plus 2 times 3, which is 12, plus 3 squared, which is 9. Adding these up, for plus 12 plus 9 equals 25. Both sides are equal. Let's try another example. This time, let's use it equals -1 and b equals 4. On the left side, -1 plus 4 is 3, and 3 squared is 9. On the right side, -1 squared is 1 plus 2 times -1 times 4, which is -8 plus 4 squared, which is 16. Adding these up, 1 minus 8 plus 16 equals 9. Once again, both sides are equal. Another important type of identity is the trigonometric identity. A famous example is sine squared theta plus cosine squared theta equals 1. This can be visualized using the unit circle, where for any angle theta, the square of the sine and cosine coordinates always sum to 1. To summarize, identities are equations that are always true for all valid values of their variables. They are fundamental tools in mathematics that help us manipulate and simplify expressions. Common examples include algebraic identities like the square of a binomial and trigonometric identities like sine squared plus cosine squared equals 1. Let's solve this partial fractions problem step by step. We need to find the values of a and b when 5x minus 4 divided by the product of x minus 4 and x plus 2 equals a over x minus 4 plus b over x plus 2. To solve this, we'll first multiply both sides by the common denominator, which is x minus 4 times x plus 2. This will clear the fractions. When we multiply, the left side simplifies to just 5x minus 4, and on the right side, we get a times x plus 2 plus b times x minus 4. Now, we'll use a clever trick to find a and b. When x equals 4, the term with b disappears because x minus 4 becomes 0. Let's substitute x equals 4 into our equation. This simplifies to 20 minus 4 equals 6a plus 0, or 16 equals 6a. Therefore, a equals 16 over 6, which simplifies to 8/3. Similarly, we can find b by setting x equal to -2. This makes the term with a disappear. Let's substitute x equals -2 into our equation. This simplifies to -10 minus 4 equals 0 plus -6b, or -14 equals -6b. Therefore, b equals -14 over -6, which simplifies to 7/3. Therefore, our final answer is that a equals 8/3 and b equals 7/3. You can verify this answer by substituting these values back into the original equation. The key to solving partial fractions problems like this is to choose special values of x that make terms disappear, making it easier to solve for the unknown coefficients. Welcome! Today we'll learn about bijective functions. A bijective function, also known as a bijection or a one-to-one correspondence, is a function that has some special properties. Let's start with the formal definition. A function f from set A to set B is bijective if it is both injective, one-to-one, and surjective, onto. Let's break this down. First, a function is injective, or one-to-one, if each element in the codomain B is mapped to by at most one element in the domain A. In other words, different elements in A must map to different elements in B. Second, a function is surjective, or onto if every element in the codomain B is mapped to by at least one element in the domain A. This means every element in B must be hit by some element from A. Let's look at a simple example of a bijective function. Consider f(x) equals 2x plus 1 from the real numbers to the real numbers. This function is bijective because, first, it's injective, different inputs always give different outputs. Second, it's surjective, every real number can be reached as an output by some input. To summarize, a bijective function is both one-to-one and onto, meaning each element in the domain maps to exactly one unique element in the codomain, and every element in the codomain is mapped to by exactly one element in the domain. This creates a perfect pairing between the sets A and B. Let's solve this problem involving set intersection. We need to find the intersection of X and Y, where X is the empty set, and Y is Z plus the set of positive integers. Let's visualize these sets. First, we have set X, which is the empty set. This means it contains no elements at all. And set Y contains all positive integers, 1, 2, 3, and so on. Now, when we find the intersection of two sets, we're looking for elements that are common to both sets. Since the empty set has no elements, there can't be any elements in common between X and Y. This illustrates a key property of set theory. The intersection of any set with the empty set is always the empty set. Therefore, our final answer is that X intersection Y equals the empty set. We can write this formally as the intersection of the empty set and Z plus equals the empty set. This is because no matter what elements are in the second set, if we're intersecting with the empty set, the result will always be empty. This problem demonstrates how the empty set behaves in set operations, particularly in intersections. Remember, when intersecting with the empty set, the result is always the empty set. Let's solve this ordered pair problem. We're given that the ordered pair a -4, b -2 equals 2, 1. When two ordered pairs are equal, their corresponding components must be equal. This means that a -4 equals 2 and b -2 equals 1. Let's solve for a first. To solve for A, we add 4 to both sides of the equation. This gives us a equals 6. Now let's solve for B. To solve for B, we add 2 to both sides of the equation. This gives us b equals 3. Let's verify our solution by substituting these values back into the original equation. When we substitute a equals 6 and b equals 3, we get 6 minus 4, 3 minus 2 equals 2, 1, which is our original right-hand side. Let's visualize this solution on a coordinate plane. The point 2, 1 represents where our solution lies. And when we use a equals 6 and b equals 3 in the original expression of -4, b -2, we get the same point. Therefore, our final answer is at equals 6 and b equals 3. Let's solve a problem involving binary relations. Given the set Y equals -2, 1, and 2, we need to find two binary relations for Y cross Y. First, let's find the Cartesian product Y cross Y. This consists of all ordered pairs where we take each element from Y and pair it with every element from Y again. Let's define our first relation, R1, as the set of all ordered pairs where the first number is less than the second number. This gives us the pairs -2, 1, -2, 2, and 1, 2. For our second relation, R2, let's take all ordered pairs where the first number equals the second number. This gives us the pairs -2, -2, 1, 1, and 2, 2. Therefore, our two binary relations are R1, the set of ordered pairs where the first number is less than the second number, and R2, the set of ordered pairs where the first number equals the second number. Welcome. Today we'll learn about the arithmetic mean, commonly known as the average. The arithmetic mean is defined as the sum of all numbers in a dataset divided by the count of numbers in that dataset. Let's look at a simple example. Suppose we have 5 numbers, 2, 4, 6, 8, and 10. To find their arithmetic mean, first we add them all up. 2 plus 4 plus 6 plus 8 plus 10 equals 30. Then we divide by the count of numbers, which is 5. 30 divided by 5 equals 6. Let's visualize this on a number line. Here are our 5 numbers. Notice that the arithmetic mean, 6, lies exactly in the middle of all these numbers. Let's look at a real-world example. Suppose a student got these test scores, 95, 87, 92, 88, and 93. Adding these up, 95 plus 87 plus 92 plus 88 plus 93 equals 455. Dividing by 5 gives us an arithmetic mean of 91. The arithmetic mean helps us find the central value in a dataset. It's commonly used in statistics, grades, and many other real-world applications. Remember, just add up all the numbers and divide by how many numbers there are. Welcome. Today we'll find the geometric mean of the numbers 2, 4, and 8. The geometric mean is found by multiplying all the numbers together, and then taking the nth root, where n is the number of values. In this case, since we have 3 numbers, we'll multiply them together and take the cube root. Let's visualize this step by step. First, let's multiply 2 times 4 times 8. This gives us 64. Now we need to take the cube root of 64. The cube root asks, what number, when cubed, equals 64? Since 4 cubed equals 64, the cube root of 64 is 4. Let's verify this is correct. 4 is indeed the geometric mean, because it's the middle value in our sequence, where each number is twice the previous number. 2 times 2 equals 4, and 4 times 2 equals 8. Therefore, the geometric mean of 2, 4, and 8 is 4. Welcome. Today we'll learn how to find the range of a dataset by solving an example problem. Let's look at our problem. We need to find the range of the following weights of students: 112, 109, 84, 89, 77, 104, 74, 97, 51, 59, 103, and 62. To find the range, we need to follow 2 steps. First, identify the largest and smallest values in the dataset. Then, subtract the smallest value from the largest value. Let's organize our data from smallest to largest to make it easier to identify these values. Here's our sorted list: 51, 59, 62, 74, 77, 84, 89, 97, 103, 104, 109, and 112. Now we can easily see that the smallest value is 51 and the largest value is 112. To find the range, we subtract the smallest value from the largest value. 112 minus 51 equals 61. Let's visualize this range on a number line. The range represents the spread of our data from 51 to 112. This distance of 61 units shows how spread out our data points are. Therefore, the range of the student weights is 61. This means the difference between the heaviest and lightest student weights is 61.